Download this code from codegive.com, link in the description below. OK, let's dive into the Jepsen 13 analysis by Kingsbury, aphyr, from Yo. 2020. This is a deep dive into distributed systems guarantees, testing frameworks, and the philosophy behind ensuring data integrity in the face of network partitions, crashes, and other real-world failures. Understanding the context, Jepsen and distributed systems. Jepsen's purpose. Jepsen is not just a testing tool, it's a philosophy and a methodology for rigorously analyzing the safety properties of distributed databases and systems. The core question is, what happens when things go wrong in a distributed system, and how can we be absolutely sure that our data remains consistent and correct, even in the presence of failures? Distributed systems complexity. Distributed systems are inherently complex because they involve multiple nodes/machines, network communication between those nodes, independent clocks that are not perfectly synchronized, possible node crashes or network partitions, the need to agree on shared state, example a single version of a piece of data. Safety versus liveness. These are two fundamental properties of distributed systems. Safety. Nothing bad ever happens. This means maintaining data integrity, consistency, and correctness. Examples: no data loss, no corrupted data, no duplicate keys in a database, no violation of business rules, example double spending money. Liveness. Something good eventually happens. This means that the system is responsive and provides a service. Examples: requests eventually get a response. Data is eventually replicated to other nodes. The system eventually recovers from a crash. Jepsen primarily focuses on safety properties. While liveness is important for usability, safety is paramount to prevent data corruption. Consistency models. Different distributed systems offer different guarantees about how data will be visible across the cluster. Some common models include linearizability. The strongest consistency model. Operations appear to execute atomically as if they happened at a single point in time. Sequential consistency. All operations are executed in some sequential order that is consistent with the program order on each individual processor. Causal consistency. Operations that are causally related are seen by all processes in the same order. Read your writes consistency. A process will always see the result of its own writes. Eventual consistency. The weakest consistency model. Data eventually becomes consistent, but in the meantime, different nodes may have different versions. Choosing the right consistency model is a trade-off between performance, availability, and data consistency. Stronger consistency models, like linearizability, are more difficult to achieve, often requiring more communication and coordination between nodes, which can impact performance and availability. 2. Kingsbury, aphyr, and Jepsen tests. Aphyr's approach. Aphyr's approach is to use a combination of fault injection, simulating failures, and careful monitoring of the system's behavior to verify its safety properties. He's not just looking for crashes, he's looking for subtle data corruption or violations of the system's advertised consistency model. How Jepsen tests work. General overview. 1. Setup. Spin up a cluster of nodes, example using virtual machines or Docker. 2. Client operations. Start a set of client processes that perform operations on the distributed system, example writing, reading, updating data. 3. Fault injection. Introduce failures into the system. Asterisk network partitions, disconnecting nodes from each other. Asterisk node crashes, killing processes. Asterisk clock skew, simulating clocks drifting out of sync. For monitoring asterisk record all client operations, requests and responses, and any relevant system events. 5. Analysis asterisk after the test runs, analyze the log data to determine if any safety violations occurred. This often involves writing custom analysis code to check for inconsistencies or unexpected behavior. 3. Yo. 2020, Key Themes and Insights. The Yo. 2020 talk highlights several important themes. 1. The importance of models asterisk it emphasizes the crucial role of having a precise, formal model of how the distributed system is supposed to behave. This model defines what constitutes correctness. Without a clear model, it's impossible to reason about safety. The model should include consistency models. 2. Fault models and assumptions asterisk understanding the possible failure modes, fault model, of the system and making explicit assumptions about those failures is essential. The fault model should include network partitions, node failures, clock skew, message loss, and corruption. 3. The perils of time asterisk the talk heavily focuses on the challenges posed by imperfect clocks in distributed systems. Physical clocks, even those synchronized with NTP, are not perfectly accurate. Clock skew, the difference in time between different clocks, can lead to violations of consistency, especially in systems that rely on time for ordering or concurrency control, example using timestamps for conflict resolution. 4. Testing as verification asterisk Jepsen tests are not just about finding bugs, they're about providing evidence that the system adheres to its specified safety properties under various failure conditions. 5. The CAP theorem misconception asterisk Kyle argues that the CAP theorem, consistency, availability, partition tolerance, is often misunderstood and misapplied. The theorem is a statement about trade-offs, but it doesn't give you specific guidance on how to design a safe distributed system. He states that you need to be both consistent and available while in a partition. 6. The need for rigorous analysis asterisk he advocates for the use of formal methods, mathematical techniques for verifying the correctness of systems, to complement testing. 4. Code example, illustrative, simplified. While a full Jepsen test is a complex piece of software, let's look at a simplified example to illustrate the basic concepts. This example is in Clojure, the language Jepsen uses, and demonstrates a simple register operation. Explanation asterisk. Asterisk namespaces asterisk imports necessary Jepsen and Clojure libraries. Asterisk mydb asterisk defines how to set up, tear down, and run commands on the database nodes. In a real Jepsen test, this would involve installing the database software, configuring it, and starting/stopping the service. The OS command function is extremely important to run commands such as installing packages or stopping processes. Asterisk register client asterisk defines a client that performs read, write, and compare and swap operations on a shared register, an atom in Clojure. Asterisk workload asterisk generates a stream of operations, reads, writes, for the client to perform. The gen/mix allows you to specify the mixture of operations you want to perform and the client/with client attaches those operations to the client. Asterisk register checker asterisk analyzes the history of operations to see if the register's value was ever in an inconsistent state. This checks if all read operations return the same value. Asterisk random halves asterisk randomly divides the nodes into two groups, which will be partitioned from each other. Asterisk partitioner asterisk generates iptables commands to create a network partition, isolating the two groups of nodes. It is important to wait before and after the partition command to allow for the iptables command to take effect. Nemesis strategy defines a strategy for injecting faults, in this case, network partitions, during the test. It uses a combination of starting and stopping partitions. MyTest creates the Jepsen test configuration, specifying the nodes, database, client, Nemesis, model, and checker. Main runs the Jepsen test. How to run, conceptual. 1. Install Java and Lineingen *. You'll need Java and Lineingen, a Clojure build tool. 2. Create a project *. Create a Lineingen project. 3. Add Jepsen as a dependency *. Add Jepsen as a dependency in your project.clj file. 4. Place the code *. Put the code into a Clojure source file within your project, example src/my_jepsen_test.clj. 5. Run the test *. Use Lineingen to run the main function. Important notes *. This is a simplified example. A real Jepsen test for a database like Cassandra or ECT would be much more complex, involving interacting with the database's API. Handling more complex fault scenarios, example node crashes, clock skew. Writing more sophisticated analysis code to detect subtle consistency violations. Real Jepsen tests often use SSH to interact with the database and inject failures. This example focuses on a single register. Real-world databases have more complex data structures and operations. The checker is crucial. The checker is the heart of the Jepsen test. It's responsible for determining whether the system behaved correctly. Key takeaways. Data safety is paramount. Focus on ensuring data integrity, even in the face of failures. Define your model. Have a clear and precise model of how your distributed system is supposed to behave. Consider your fault model. Think about the possible failure modes and design your system to be resilient to those failures. Test rigorously. Use tools like Jepsen to inject faults and verify that your system adheres to its safety properties. Understand consistency models. Choose the right consistency model for your application, balancing performance, availability, and data consistency. Be aware of time. Imperfect clocks can introduce subtle consistency problems. Formal methods can help. Consider using formal methods to verify the correctness of your system. Remember that Jepsen is a powerful tool, but it's not a silver bullet. It requires a deep understanding of distributed systems principles and careful design of the tests. The Yo 2020 talk is an excellent starting point for learning more about Jepsen and how to build safe and reliable distributed systems.